I'd like to thank everyone for attending the event today. It's exciting to do this virtually. My name is Kirk Haslbeck. I'm a principal data scientist at Hortonworks. I want to talk about the exciting topic of data science, but more importantly, how to be productive with data science and how companies are transitioning from one-off data science projects to becoming data science ready in every avenue of their business. We're moving away from the days where data science is a project here or there or in one case, and obviously into the days where it'll be a part of every business use case. Quick background on myself. Prior to my days at Hortonworks, I spent about a decade on Wall Street doing predictive modeling, things like insider trading, financial crimes. I have degrees in both computer science and data mining, machine learning, and it gives me an interesting perspective on the topic when we have to balance things like programming and efficiency, as well as accuracy of the results, findings in the data, letting the data tell us the story. So for the last couple of years, I've been working at Hortonworks with our largest customers around how to become a data science practice. So it's sort of that maturity level from where we start getting good at data science and we see it work once or twice to how do we rinse and repeat this process and do it in a way that we're not re-implementing the models in different languages. How do we become, whether it's platform ready, container ready, all of those things. So hopefully today I have a lot of material. We can bounce around to the most interesting pieces, but I'm going to start by level setting why that's so important, but we are going to get into real models, real problems, and hopefully bring it all the way into why data science is really becoming a platform decision. So I like to take both an academic point of view as well as a practitioner point of view, leveraging my decade or so of experience. I have about 100 models in production in other areas of financial crimes and things of that nature. So with that, let me jump in to this slide. Yeah, so I like to start with this slide. I'm actually going to bring it back up again in the future, and you know, in a second here, I'm going to focus a little more on this machine, so I might kill the webcam. But data science becomes a platform decision, and you can start to see that here because, you know, in the first step, we would need to store a lot of data to have holistic insights and to do it at the right cost. And that has become possible with things like HDFS file systems. There's also object stores and other things out there on the market, but largely Hadoop is, you know, a dominant force in the market of at the right cost with the right fault tolerance and distribution. How can we store and amass a lot of data? But we always have to face security challenges. So we need to be secure all of the time, and we need a component like Ranger that can look across every element in the stack. So whether I decide to attack the data science problem with Hive or Pig or mainly Spark in a lot of cases, no matter what the method is, we need security that you cannot circumvent in all of those cases. And Ranger satisfies that need very well. Beyond that, we need to govern the data. So where did it move to and from the lineage? How does the metadata around it look? And how can I share the data left to right? All of these things become important in that story. So gaining access to the data. And then finally, we would actually want to run our fancy algorithms, which we'll talk about a lot today. On top of the data, we might choose an engine like Spark that would be distributed and fault tolerant, but very compute oriented for machine learning algorithms. And then we would need to visualize and collaborate on top of the data. And I'll show tools like Zeppelin and DSX to give us a rich workbench for those environments. So this is sort of the level set placemat of already why this becomes a platform decision. So many companies are on a journey from gathering data, storing it, all the way through to predictive analytics. And that's sort of the destination is at some point, how do you get the most business value out of your data? And once again, not one time or in a single project in a language like Python or R, which would be fine, but in one place, but on the platform itself. We want to try to cover both actionable intelligence from data at rest and in motion. So when we think about that, a lot of times we're just training on large data sets at rest, but I'm going to show today a model in real time actually hitting either a Kafka queue or RESTful endpoint, and that we're actually tracking and monitoring the behavior of that model. Is it doing what we thought it was doing when we released it to production? How's the performance of the model, and how easy it is to hook into it? But we need to be thinking about both at rest and in motion for true actionable insights. Another big consideration is the cost of the disk and the storage. So the costs are constantly changing, so I'm not going to kind of die on this slide by any means, but ultimately, to get more insights, more holistic insights, we want to be thinking about how to store and amass more data, especially when we're looking at real-time and IoT. The data volumes can get pretty high pretty quick. There's an advantage to being able to store more data, more scalable at a lower cost for sure. So all of that information sort of leads up to this picture, and it's this whole picture of produce more valuable and holistic insights, but we can't forget about security and policies of every silo, so we need something to manage all of those policies. We need to be able to collaborate. All good data science teams, right, are not just standing around over somebody's shoulder anymore in a single maybe MATLAB desktop application, but collaborating, even if it's not in real time, but sharing the results. And we'll talk about how to push processing to the data through the notebooks, through the tools that are available out of the box, because that's going to allow us to do a lot more group collaboration and share results and ultimately drive better results. Time to market is really important because, in today's world, whether it's cyber or fraud, it's constantly changing, and we have to be able to release models and republish them into production with a reasonable time to market, or we're always chasing. So when we get into model management, once again, how does that work on a platform? Because if we're building in a one-off tool in a language that maybe C, maybe Python, maybe R, is that really the production platform that will be executing the model in? Or do we have to re-implement the model every time? If we do, that's going to eat into the time to market quite a bit. So here we're going to show how to build models and then deploy them immediately in the same environment, even if they're in a different language, whether it be containerized or something to make this operational. And then store and access the data, obviously, at the lowest cost. Another level set is to think a little bit about all the varieties of data that we face now in our challenge. So once again, as a one-off project, we may only face one of these scenarios, and we would write a specific model to handle structured data, unstructured data, or time series. But commonly I find in the teams that I've worked with and run, we have to deal with all of these scenarios, sometimes in a single model, or sometimes just different, pick your poison for different models. But we will run into structured, time series, and unstructured or semi-structured data. And it's imperative that we have a platform that can handle all of these, that we're not constantly switching again the tools in the tool set, but we're just picking the right tool for the job out of the tool set that we have. So I'm flying through this material because I know everybody's going to be hungry to get to some of the heavy data science stuff. So I just want to set a little bit more background because it's a wide audience. So we look at the timeline as a progression from descriptive to inferential statistics into machine learning. People are looking for real-time predictions all the way down to the edge. So at the point of the sale or right where the car is driving out on the road, how do we get that model that's built and trained on the massive data, but then all the way back to the edge where it may be imperative to make that prediction fast and in real time. And then deep learning truly is a different category. It is more than just machine learning. It is oftentimes ensembles of machine learning or deeper rooted algorithms, and we'll get into a little bit of that. So when we talk about descriptive statistics, we're not really doing data science or machine learning yet, but it is used in a lot of places and is a very valuable thing to use, in the sense that if we look at a famous data set for Motor Trend cars, we can see statistics like miles per gallon, cylinders, displacement, horsepower. These are all numeric variables that are describing the car, and we can break them down in a language like R very easily with summary stats and things that would show the mean, median, mode, range, standard deviation, and confidence. Oftentimes, a lot of our dashboarding tools and other tools are just fine with descriptive statistics. So there's nothing wrong with it. It's just that we're not really achieving the full data science or predictive state yet by just using descriptive statistics. And that kind of brings us into pick your favorite tool. Now, there's Tableau and Click and a million BI dashboard tools, but there's an emergence of notebooks, and they're here for a reason, because in a notebook like Zeppelin, and I'll show Jupyter and DSX later in this, we can now start to write code that's not just a widget out of the box that is provided to us by the BI tool. There are snippets where we can put machine learning algorithms in. We can chain, I'm going to show pipelines, which is a machine learning pipeline where we can stage the entire process front to back and even call it through RESTful APIs. And this gives us a lot more flexibility and allows us to write the code we need to write and push the process into the data and then interact with each other in a lightweight browser type environment. So gone are the days maybe where it had to be in Eclipse or IntelliJ, although those are still fantastic applications. They're still pulling data out of wherever it lives into your desktop on the 4 gigs of RAM that may be sitting on that machine, and is not making use of the full horsepower of a cluster where it would dwarf the amount of effort it would take to crunch that same iterative result set. So here, after we start to think about all of those things, we can start to think about a branch of machine learning called supervised learning, where we're going to infer the outcome based on labeled data, and we would use training sets, and then eventually after enough training, we could make a prediction. And ultimately, the most common one is a linear model, and it's trying to draw the best fitted linear line in between the data points. So in a language like R, we could do this very easily, shown up here in the upper right, and we would then talk about simple linear regressions versus multiple linear regressions. And in this case, if we go back to the Motor Trend cars, we could predict something like miles per gallon. And we would have to figure out through feature selection what our best features are. So we may start with a correlation matrix or something that measures the strength of the relationship. And we would ultimately have to pick cylinders, displacement, horsepower, weight. And I know in this example, you'd end up finding that weight is a big impact on the car, how heavy it is, how many miles per gallon are affected. Horsepower is also another one. So we would use some techniques to derive that information out of the data. And then finally, we can make a prediction based on this weight and this horsepower. What do we expect before we go and build this car or spend millions to prototype it, the miles per gallon rating would be? And we're finally kind of growing into, at this point, a little bit of a predictive model. So I'm also going to fly through, I think this is a funny slide for anybody who hasn't seen it, where we are in the famous category of image classification or misclassification. It's come a long way. So if any of us wanted our jobs to be, classifying images, it's probably not the right one to sign up for at this point, because we would be beaten by a machine, and machines started to win this game around 2015 or 16. And you can see now from the Silicon Valley days of hot dog, not hot dog, it's come much further than that. And there are times where even humans get a little bit stumped or confused based on the ambiguity of the image. And you can see that a machine is approaching that same level. Here's the chart that sort of shows the error rate. And after enough competitions and different neural nets that were introduced specifically for image recognition, it's grown, quite a ways to a point where it has now surpassed human recognition. So one of the cases that I think is fun to talk about, it's a big case in the industry, is preventive maintenance. So what we would do here is I'll actually walk through the steps in building this model and why it makes a difference which platform you would build it on. I love to interact with the audience. I think that this forum isn't going to work quite that way. So, if everybody wants to pretend to show their hand on how many have built a model, I would imagine there's quite a few on this call. Some of the limitations, right? So we start out and we want to build a model, and we have to think about it as we would in all of the cases that would come up in real life. So we could just build conditional statements. The problem with a conditional-based model, kind of like a decision tree, but let's be even more crude, would be that if I exceed a condition by a lot or a little bit, I often don't rank that. It's a 1 or 0 or true or false condition. So I spent more than my spending limit, or I'm outside of my spending pattern, or in this case, the vehicle or engine sensor is completely overheated or broken. There's no way to say it other than yes or no. So they definitely work. There's still a huge place for rule-based and condition-based logic, but we'll start to see that falls apart sometimes. Then we need a lot of data. So what tools can we use to amass? And right there, we'll start to run into that problem of desktop tools. So how much can you really pull in? I always feel like the data scientist sort of goes to the DBA with a gun in his hand and says, hand over all the data. I've got this top secret project. I'm about to get started. I can't tell you about it, but I need all of your data. And you right there realize, well, you can't, because you either bought a database or a big data platform because you had more data than could be stored on a desktop. It's also not a secure practice to hand it out, and immediately we start to hit the challenge of sampling. But if we were going to sample the data, and I teach a data science workshop, and one of the areas I spend a lot of time on is sampling, because we look at things like election voting, what happened in the last election. Sometimes the sample does not represent the population or what will actually happen in production, so to speak. So it can actually take as much or more time to sample the data and have an accurate sample to build your model on as it would to just build the model itself. So now we've kind of covered the security concerns, the limitations of compute, as well as the downsampling, and then finally collaboration, right? In the traditional environments, if we're going to pull data out of a database or wherever it lives and put it somewhere, we've now kind of violated all of these principles. So there must be a better way, so to speak. If we think about trying to solve a preventive maintenance problem, we would have to look to which model should we choose. There are plenty of options. So if we're thinking about making a prediction about engine failure, then a logistic regression might fit, because we really need to know if it's going to fail or not, or if it's about to fail. So that could be one way to pick the model. The other thing that'll happen right after we kick this one off is I ran the model, but did it work? Oftentimes, strings and categorical values are not the expected input, because just because you can run a model or get it to run, we have to diagnose the output and what the model is really trying to do to figure out if the model's behaving properly and actually giving us the results that we would expect. So that's kind of where we transition from data science 101 to, oh, I actually have to pay attention to the model, and that part gets a little bit mathematical and sometimes not as much fun as getting started. Which feature should I choose, right? Then there's this whole category of feature selection. Just sending all of the features into the model is usually not the right pick, so we actually have to go through a process of feature selection and techniques that will help us do that. I want to switch over to the actual code here. I'm going to try to do it. I apologize if it's disruptive at all. Oh, I see Brazil, I see some USA, very cool. What we might want to do is move into a notebook tool such as Zeppelin. And Zeppelin gives us the ability to now write some code, push the processing to where the data lives. It's easier to move code than it is data in this world. So Spark is the engine of choice for this example, and I could read from a database or a CSV file And there's some formatting that needed to be done on the timestamps, as usual. Of course, if anybody's ever dealt with time, there was some malformed records and some other things. But there's a lot of really cool visual plugins. So maybe I want to geolocate all of the vehicles in the field, or it could be sensors in a factory, depending on the image that I want to use, or how I want to see the graphic, because it's all about telling a data science story, right? Next, I did a correlation matrix. And what I found here was that I had different results from different breeds of correlations. And I felt that this one was better because the default Pearson's correlation often just looks at discrete variables. But I have continuous variables like miles since last service, and they're constantly growing or changing. And I felt that this correlation gave me a more realistic perspective of the relationships in the data. And that's really what I'm looking for here. My first problem is, which features should I pick? That does introduce bias, and it is supervised learning. So right there, I know there's some red flags go off, but we'll argue later about supervised versus unsupervised, and I think we'll find that supervised is still a very popular choice in cases like this. My data actually came in maybe as events, like JSON or XML, things of that nature. But the first thing I like to do is convert it to tabular format and see it in a table that I can get my hands on, right? So this can visually validate. There's obviously very good ways to validate data, but at a first glance, before we clean the data, and I can see my timestamps are uneven, and all kinds of other things could go on, maybe numerics and strings that get mixed up. So ultimately, maybe my first challenge, and I'm going to try to toggle it here and see how this works, is time series machine data is not so clean. And we have to sit here and look at the sensors and the time, and now we have to resample the data, and there are also more non-failed events than failure events. So these are the first two challenges we will face right away in almost any data science problem, fraud problem, sensor problem. And so ultimately, I am a co-author of a library called Scythe, which is a distributed Spark-based time series library. But even without that library, we could use some SQL techniques and other things to resample these times into time bins and even intervals. By doing that, I'm sort of downsampling into trips or route segments, and that's going to allow me to do two things: boost the failed events, because now if there's a failure anywhere along that route, I'm not really sitting there going, not failed, not failed, not failed, not failed a million times until it's a failure. I'm going to first downsample into trips and routes, boost the failure signals, and then also have even time intervals. I then found that I needed to derive or compute another column, that it would be better to step interpolate, if you see over here, miles since last service, into a bin. It didn't really matter that it was 5,001 miles or 5,002 miles since last service. It mattered more that it was 5,000, 6,000, 7,000. There was a point in which the vehicle probably needed service or was going to have some sort of slowdown failure or become less reliable. So by computing and deriving other calculated fields, I could then decide if those features became the better feature to be trained on. Then just basic descriptive stats, what we covered already. You may want to see if the makes and models that you've covered here. So part of the data science process nowadays isn't just to write a model. People are being very particular about, did you cover all the classes of vehicles? Did you cover all the segments of individual drivers, the races, the age? People don't want the models to have these discriminations in them anymore. So even just simple descriptive stats can solve that problem in the notebook. And once again, unlike a kind of a code editor tool alone, you're not going to be able to paint this story for the business, for the user. So I like to think of these notebooks as a transparency tool. It helps me walk through with a business analyst and say, no, we covered Chevy, we covered Ford. You're right, we're missing Toyota or whatever that might be. And we have all of the drivers for. And then I realized model was not really behaving properly on the strings, categorical variables, and brands. So to do that, we needed to use a feature called one-hot encoding. This would take a string, index it, and then make a vector out of it, basically, so that the machine can understand in the form of numbers what are really so here I was able to write this code right in the notebook. So once again, far different from a BI tool. This gives us completely different flexibility and abilities to pick and choose the code, the languages that we want to use. And by doing that, I could actually figure out which makes and models were more fault tolerant or were going to cause more problems. Eventually, I could get to the point to train a model, and we would go through the logistic regression that we talked about, split up the training set. You want to hide certain pieces of the data often from your training to your production, because in real production, you are going to see different data that was not in your training set. Eventually, you want to build up, describe those training errors, and then oftentimes people describe the output of a model as a ROC curve, and that is the number of true positives over false positives. So you can sort of see the accuracy grading. The confusion matrix is more complicated than that. I actually prefer it better, but it's how many trues became false, how many falses became trues, and it's really more of a 4-quadrant. But people sometimes divide those, get the rates, and show it in this way. You can see the difference in correlation here and the use of categorical variables. I built 2 models, pitted them against each other. And by doing some of those techniques, I was able to eke out, from about 90% accurate, almost up to 100. Truth be told, of course, anytime you're doing these one-off examples like this, I am overfitting the model, right? So I don't want to actually brag too much here about this accuracy. It's because I've spent so much time on this data set, and every one of these features that, yes, it was accurate at this moment, but in real life, we would see this not be quite this accurate, at least in my experience of all the models I produce in production. There is a rate of decay, and that's where we're going to get into model management here in a minute of how do we really know how they actually perform, not how we thought they were performing. Everybody believes their model performs perfectly when they tested it. Here is a visual illustration of some of the challenges that I went through building this, and I think it might tell the story a little bit more clean, the make and model, how we would index and one-hot encode those. This is the same model, but in DSX instead of Zeppelin, and I will show this in a minute as we get into the model management aspect. And basically, it's this life cycle that we're going to keep repeating as data scientists, especially at scale. And it's this life cycle that matters so much, because if I need to visualize, load, and train, as we did in that iteration, and we may do this again and again and again, do I want to keep re-implementing the model? Do I want to keep resampling the data? Do I want to keep worrying about those things? In this case, I was able to do this so quickly because the data was always living either in HDFS as a file or in Hive as a table. And Spark is natively integrated with those technologies. So really all of those iterative result sets in machine learning were done on the native platform in development, but could be moved to QA or production without ever re-implementing or changing the model. To me, that was very important. When I ran a team of 50 data scientists and engineers, we were always sitting with each other saying, how do we rewrite that neural net or this proprietary thing or what he did in this tool? And the reality was we never really could rewrite it easily or accurately in another tool. It was more of a waste of time. So this is a recap, but I think I beat it to death, so I'm gonna skip over here. And then this also goes back in case we kind of lost track of that first slide, which is the data being on HDFS was secure the whole time. It was governed the whole time, although we haven't talked too much about that. We use Spark there with machine learning libraries and different ways to compute, and Zeppelin to visualize the problem, and it was a pretty nice, efficient way to do it. So the next one that we could talk about, with some similar challenges would be a fraud use case. And let me jump over. I'm going to try to show the code again. Slide over to this monitor. Before we jump in, it's always good to remember that all models are wrong. Some are useful. This is sort of my favorite quote to not get too depressed while we try to make the perfect model. I also like to start out with the requirements of a model. So, before we get started, what is the goal? Just building a model for the sake of building it is often kind of how things get started, and then the expected results aren't there at the end. Or it was, we sort of had unrealistic expectations and goals of what the outcome would be. So the requirement in this case might be to detect fraudulent transactions. The goal would be to save the credit card company money, to build trust, to cut down on fraudulent crime and insurance. And then we might have a functional requirement to detect fraud in under 2 seconds at the point of sale, learn and adapt, and make smarter decisions over time. The 3 features that I would derive for something like this would be distance, how far one can travel over a period of time before a transaction is fraudulent. The category, someone like myself might shop at a Men's Warehouse or something like that and not Forever 21. So there are different ways to maybe look at those types of patterns, and frequency of how often I make purchases, the time between them, and the amount of purchases I make. There are many other features we could derive, but those to me would stand out as a pretty good baseline to get started. We would then have to be thinking once again about how does conditional logic play into this? Well, it does in some areas, but in areas such as I make a purchase in Maryland and then I make a purchase in California, I don't really want a matrix of every state, county, distance of what is right or wrong. So Boolean logic probably isn't going to fit there. Where it might fit is in simple conditions like, is he trying to make a purchase greater than his spending limit? I would say that is 1 or 2 lines of code that are 100% accurate, extremely efficient, and not worth training a model on. So you'll see over time a blend maybe of different types of code that make their way into what I would call the entire model. It's not all about just the predictive model somewhere in the chain. So there's a good use and example of statistics, machine learning, as well as rules. But what we ultimately need and need to be thinking about is the feedback loop. Isn't it really all based on putting something out there that can be forever getting smarter? And that's what we did in this case. So when I first gathered all of the data and transactions, they didn't make any sense. What happened was they were all over the place. And here, I'll show you actually at this point. Let me just jump over to the screen. So the transactions came in JSON format. And that's not really the way that the algorithms we wanted to use accept data. So in one line of Spark on this platform, I'm able to do a massive kind of transpose or pivot into tabular format, which I can show here, which is largely helpful to get started. So here now we have event data coming in from Apache NiFi, which I'll show in a minute, and I can automatically convert that into tabular format to get started. I once again like to see a breakdown descriptively of the statistics and what my coverage is, how many accounts am I getting, and what the spending categories are in this case. But I'll skip some of this breakdown. But what we got was this, and we called it pointillism to be a little bit cheeky. There was nothing that I could do to make a good prediction out of this data, and it's important to kind of understand that so that we can reshape the data a little bit. Ultimately, until I kind of took some different approaches in shaping here, I wasn't able to see a norm or anything that I thought would represent a repeatable process. So I had to use the same process that I think a lot of the actual companies do use, which is to classify and categorize the purchases by putting them into categories such as entertainment, gas, convenience store, grocery shopping. And by doing that, all of a sudden, you start to see that it's very clear down here what the pattern is in this section, up here as well. And it's actually only in the middle ground here where I think the model could get confused more so than anywhere else. So interesting visuals to be able to understand that. And then we would once again come down, train the model. But see, at this point, what we're able to do is call model.save when we're happy with it, and write it to disk, read it back into any environment, or publish it so that it could be run under management. And that's kind of where I'm going to go with this in 1 second here. But after doing this, shaping the data, profiling the data, I was able to get the normal behavior for every person, every account, and the way they behave. And then by graphing it in this way, you could see that I take the train the model on basically the anomalies and profiles, and I can get a standout of when they're outside their behavior. And what this told me was a traveling salesman, such sometimes as myself, it's normal for me to travel from Maryland to California or spend money somewhere else. It is not normal for someone else who is a local, maybe grandparent that walks to the market and stays local, doesn't travel that much, or has different patterns where I spend money versus where someone else spends money. And by doing it that way, I built a behavioral engine and trained the model on those behaviors, and it was very accurate for a while. We left it up and running, but to get it running back then, we had to build a container called Slider, put it on Yarn, worked pretty well, and I'll show it here in a second. But today there's an easier option for that. So already we can do all of this in DSX, which is I'm leading up to here. So to actually make this a true machine learning feedback loop at point of sale, we had to build the mobile app and a web app, and then I had to launch the web app on in the cluster, and we started getting an inbox of feeds of real time. It would show us things like the distance between the transactions, and I could show outliers. And then ultimately what we would do is we would suspend the account, and on the person's mobile app at point of sale, it would pop up and ask them if they've made this purchase. Based on their response here of yes or no, we would actually retrain the feedback loop, and the model is still getting smarter. It's done pretty well. It's been tested in a lot of accounts at this point. But we're not here actually advertising a credit card model, but just how to connect the whole machine learning feedback loop so that we can bring the analyst into the picture. We can bring people to the problem. It's not just about the algorithm. And to glue all this together, we used Hortonworks data flow, which is built on Apache NiFi, and we were able to listen to all of the transactions on SQS queues, and able to transform the JSON, push them out to the web app or through to the application. So Apache NiFi was a very good and easy way for us to drag and drop and connect the platform in real time. But what I would like to jump over to now is how I would do that today. Because that was just a year ago, and technology is moving so fast. That in the Hortonworks Data Science Workshop, we do a flight predictor in real time. Well, first, it wasn't real time, right? Like all models. We had to sit there and learn what was the right prediction. We had to go through the same process that I'm going to pass through quickly here now. But if it was a weekday or a weekend, build up our own features, we would extract departure hours and try to figure out what we thought was important to the model. And as we go through and build it up, there was a couple different models that were trained and tested, and I'm going to show them here. Here's some of the feature handling still. And then at this point, random forest and a generalized regression model. And there's a concept of a pipeline that becomes so important. So how do we actually start testing the models with the raw input data and not the numerics or feature vectors that feed them? Once again, if we build these as one-off products and projects, it's up to the data scientist himself, sort of how he crafts it and what the model is really going to do and what data he feeds it at which stage. But if we start committing to this idea of a pipeline, we can get away from all the things that happen through the transformations of the model and go right from the end to the output, or I should say from the input really to the output. And that way now we can connect to something like Apache NiFi and literally send it the raw data right from the airlines, right from the weather station, and let the model continue to do the transitioning steps. So that's a key element here. And by doing that, at the very end, you're going to see some interesting code. But what this is doing is registering the model automatically in DSX's model management system and giving us a URL here to be able to hit it as a RESTful endpoint. So ultimately, from a curl command, this is an example. Now, if this confuses anybody, I actually just moved from Spark to Shell. This is the capability and flexibility of a notebook, where this is Python Spark in one snippet, and this is Shell. So I'm assuming the audience is probably a little bit advanced in this case, but notebooks are extremely powerful. And here we just built and tested a model, but now I want to show as if I was right down at the command line, which we could be, I could run something as simple as a curl, which would be completely separate and agnostic to this, and it's just a REST interface. We have a bearer token for authentication, so only somebody that has this token would be able to ask the model if it would predict that this flight would be delayed or not, right? And we would get our prediction back. So this whole framework now, if we come into here, there's a Hortonworks Data Science Workshop project. We created a notebook. That's the one we were just looking at, the Python flight predictor. But we also ended up deploying it as a model. And now this starts to make it easier than, well, did I have to build a web page? How do I test the model? How's the model performing? Where is it running? All of those nuances are taken care of here, where we can say flight predictor has been deployed by Kirk. The API has been called 86 times. So someone, myself and others are actually calling this API. And then ultimately, let me see if I can refresh this. Yep. And I'll go into a tool like NiFi, where it's getting the data in real time, it's flowing through the process, and it's calling invoke HTTP. What we can see here, try to make this box a little bigger, is this is the RESTful endpoint that was provided from DSX's model management. And we can hit this in any data flow, any application. In this case, we want to do it more near real time, so we're using a tool like NiFi, which makes it very easy for us to kind of string all of these things together. And by putting that endpoint in here, we not only now built a model, trained a model, could save the model, but we could publish it as well as provide a RESTful endpoint back to ask the model questions. And then you often have to wonder at that point, well, how is the model performing while all of these people are asking you questions, right? So we now have these metrics of the model and the deployments to look into. Here in DSX, you can see the RESTful endpoint that was published. It provides you the bearer token of the deployment so that you have the right security and authentication. You can see here the columns of the input schema. Once again, right, because of that interesting concept of a pipeline, we're all the way out to not necessarily the features and the vector, but the actual raw input value. So this gives someone like a layman or citizen to come in here, call the test API, and actually play with the prediction level by just entering in. Maybe they want to test if BWI to San Fran Airport would cause a delay at this time. They can hit the same RESTful endpoint API here. So hopefully that starts to bring it full circle into what the picture really looks like, which is an environment to do data science in. It doesn't matter now if it's Scala, Python, or R. All of them are supported. Pick your favorite notebook, Jupyter, Zeppelin, RStudio. But the fact that they're run computationally on Spark and all the security implementations of Ranger are being handled, the fact that HDFS can store unlimited amounts of data and a tool like NiFi can help connect you to these environments, we can now really solve the whole problem again and again in a repeatable fashion. And then ultimately, I'd say really part of the newest link in the chain is model management, to have some more insight into it's not just a process that's running somewhere on a box, but it's a process that we understand the performance of, and we can test the inputs and outputs too. Ultimately, this process becomes repeatable because of the platform and the tools that you can pick, because Zeppelin or DSX, right, would sit and allow this collaboration, but all of these other components here on the screen really have to be put in place to enable this to become a common collaborative platform and to continue to push the processing through the data. With that said, I hope everybody enjoyed the talk. Feel free to reach out to me, K. Haslbeck at Hortonworks. I'll leave the information in the slides. I do a lot of local meetups and data science workshops and talk tracks. So if yourself or company or anybody wants to go through a rich example of how to solve one of these problems in an industry, soup to nuts, and all the tools that we think would be required to string together quickly, the HDP platform and HDF are open source. They can be downloaded from the sandbox. DSX is offered by IBM, which is a full partner and integration. So everything I showed here can be done today, and I'm happy to come work with any group on solving these problems. I do love the call outs. I see Brazil and Canada and people that are liking Zeppelin. So it's hard for me to keep the webcam and all of the slides going at the same time, but I like the energy. It's very cool. And I actually am a big fan of Zeppelin and Scala, but we could debate Python versus Scala all day long. So I don't want to hurt anybody's feelings. Yeah, so the code, actually, I saw this question come through. I publish all of my stuff. Let me just give some example links here. Kirk has GitHub. Pretty much everything I show is available. I'll paste it into the chat here in a minute. This is a good point. I run the data science workshop for Hortonworks. So like I said, my services are ready and available to come out and meet with anybody here. If you want to look at the flight predictor, we do every language in both Zeppelin and DSX, which is technically the same thing, but in DSX you can keep the data sets local instead of pull them in remotely. So we have the data sets here. We have Python, Scala, R. You can go into all the code, and as well as I keep Zeppelin notebooks. So Monte Carlo analysis is kind of a famous value at risk calculation by financial institutions. The credit fraud, golden batch is very interesting. Of course, preventive maintenance we touched on, which is a large time series problem. Predicting the best batch of medicine. So hopefully these are some cool examples. Also, if we do something like credits, fraud, guided score, Hortonworks, most of these are full articles. And they come up pretty high on the Google search. So Tom McCooch posted this one, but it is the same article I showed. It goes through all the steps, how we strung NiFi together to do predictions in real time, how we distributed the process, how we built the model, how we built the mobile app, and what that integration looks like. So some simple Google searches here. Everything I showed, it should be pretty much public and available. All right, can we get a copy of the presentation? Yes, for sure. I'm going to put it up on Box and send it to the administrators. How would process be iterated after all the feedback from production was taken in? Would you go step one and produce another model? No, so what we were doing in the credit fraud model is we were just retraining on a either nightly or weekly basis, but it turned out we didn't need to retrain all that often, because once you learn enough about the behavior, remember the credit card prediction, at least in this case, was behavioral driven. So your behavior shouldn't change all that much, and a single behavior change isn't going to completely change your predictive value. So it wasn't as though, even though we were getting the feedback in real time, that we were actually retraining the model in real time. There is a category of retraining in real time. I'll argue that it takes some thought of when you really need to do that, because if you've trained your model on enough data, a single data point or two shouldn't influence it that much. It could in a case where maybe the model's never seen those data points before, but what we did is we had an offline retraining. But the most important thing is that we're actually capturing the yeses or nos, flagging the accounts, and getting the analysts to help us drive the model to be smarter. I think that part is often forgot about. It's let's just build a program. Well, the program's about as good as we're willing to groom it and provide it clean data. What to learn as a beginner data scientist? It's a little bit broad. Yes, there we go. You can see my chats. Okay, well, it's probably a good stopping point. I think just kind of saturated the questions. I hope it was fun for everybody. I appreciate everybody attending. Like I said, find me on LinkedIn or GitHub. Beginning data scientist, you know, definitely you can download Zeppelin. It's a free tool. It's pretty cool. It would support Python and Scala. Spark has just a ton of examples, which are great in the community. The Python community is really strong in data science. We could argue, I'd have to go into more detail. I think R is actually a really good language. And then I like Scala for other production reasons, immutabilities and ACA patterns. But it's too much of a political debate to get into why we each like our own languages. But Python really has a super strong community, a lot of easy ways to get started. Hortonworks has a sandbox. It's available online if you go search Hortonworks Sandbox, where everything I showed here today is downloadable all the way down to a laptop. It runs in kind of a virtual environment or like Docker image, and you just launch it. So if you want to connect Zeppelin to NiFi to, you know, everything here and build it, we do it all the time for the sake of demos on our machines. I think that's a great way to get started and simulate an entire big data environment without having to stand up, you know, a 20-node cluster. So with that, thank you. I appreciate everybody attending. Love the shout outs. I will talk to everybody later. Feel free to reach out. Goodbye.